Good morning.
Okay, protocols will stand. Kindly place yourself on mute so we won't have any aberrant sound. If you have a question, kindly put it in the chat, and periodically, in between topics, I'll be addressing chat questions. So put the questions in like a whole sentence, because it could be a minute or two after I answer. So when people ask, can you repeat that? I don't know. It could have been something even before of what I said. Another public services announcement is what's due today. First of all, this is MED110 6DAX, which is here. A lecture, Zoom lecture at 9 a.m. Uh, I don't think the person is on here, but someone checked in at 8:15. Okay, you can, but it's 9, October 28, and this is week 3. So what's due today are all week 2 items. So what are week 2 items? Week 2 items is the task 2, discussion 2, and lesson 2. And the lesson 2 had that PowerPoint. And let me also review the discussion 2. Um, More than half of you who put up a discussion didn't read it. So just to review, when you do a discussion, it's supposed to relate to the lecture in some way. Now, what many of you did was you guys saw the word Alzheimer's and then you handed in a book report on Alzheimer's. This ain't high school. That's not what was asked. If you see here, it says use your textbook and other resources, research the topic, right? And in 2 to 3 paragraphs, what did we talk about? We talk about the chemical bonds and how to relate. And the hint that I gave you was the neurofibrillary tangles of Alzheimer's disease. And because of the chemistry of those tangles, it causes signs and symptoms. And how do we deal with the pathology? We deal with it with drugs. So another thing that other people did was, here are the 3 drugs: drug A, drug B, drug C. Okay, all well and good, but part of this class is to understand pathophysiology. How did my patient get messed up with Alzheimer's, and what are we doing chemically to reverse that? Okay, or at least to stop it. A classic example is HIV. HIV drugs do not combat HIV. Its function is to combat HIV load, a viral load, right, and to not progress the disease. And Alzheimer's, for those of us who did the discussion, Alzheimer's is a progressive disease with no cure. So something like the main drug of choice, which is donepezil. Donepezil, it only slows things down. My aunt had Alzheimer's. It bought her, I don't know, an extra 9 weeks, and still, even then, it still started to progress. And it also shows that memory is not only electrical, which we'll talk about in Anatomy and Physiology 2, the sequel, right? Memory is also chemical. So it's also the reason why, like if you drink too much, why you black out and you can't remember anything, because you altered the brain chemistry with alcohol, and alcohol, albeit a tasty drink, it is a depressant. The initial effects are always stimulation, but the overall effects are depressant. So I'm going to relook at this stuff, and kindly look at your comments, because I think many of you simply glossed over the assignment, and pretty much assumed that, oh, let's look up what Alzheimer's is. That's the easy thing to do, but to relate it to what we're doing, and that's the main point of taking this class. Not necessarily to memorize all these things, because you could easily look them up, but to understand how does anatomy, which is the parts, and physiology, how the parts work together, how do they also affect pathology, logi, study of disease. And last week, our topic was chemistry. And now we can see how chemistry helps us in the form of pharmacology and how chemistry, right? If you take my pharmacology class, the first lecture I always talk about is how anything can be a drug. Water can be a drug, and how drugs can affect you positively or negatively. And isn't that what we talked about, homeostasis? Things can either give you too much or too little, but our job is balance, and that's what medical management is, and that's our job. So that's what's due today. Task 2, discussion 2, lesson 2. And we are now in week 3, so we're going to now tackle these things. And now next week, these things are due. And remember, I have some of you giving me week 1 stuff. Sorry, that ship has sailed. Remember, we talked about in day 1 that because every day is 10%. So if you're late a week, that ate up 70% of your grade. So it's already close to 0. But I'll take it and I'll put in a score because my attitude is 30 and 40 is better than 0. But don't get into that habit because remember our first day lecture, and also the holidays are coming up. Term 5 is really rough because there's holidays coming up and there's a lot of distractions, especially those of us who have children. Or even if you don't have children, there's just a lot of stuff going on. So keep your eyes on the prize and focus. So the focus for this week is, let's look at task 3. We are now going to be looking at cell theory, right? And I know that's a goal because look, it was in red and there's a link to it. Cell structure and function. And isn't that, so cytology, the study of cells, that's all that it is. It's the cell structure and all of these little structures called organelles, and we're going to talk about that in a moment, they all have a specific function. There's this guy, Leeuwenhoek, at I think in the 1800s or something like that. He was an optometrist who figured out that if I put like 2 different glasses together, I could magnify things. So Leeuwenhoek was the father of microscopy and kind of like the guy who sparked cytology. And you'll start seeing that he called them the little beasties because in all intents and purposes, a cell is like a little animal. It eats, it processes things, it requires energy, and it poops. So, or defecates. We're in college, we got to use college terms, right? So, if our little beastie or if our little animal organism is flawed or sick, what are the odds of us getting sick? The cell gets sick, the tissue then gets sick, tissues then get sick, the organ gets sick, multiple organs get sick, and then the human being gets sick. And back to our picture, instead of me yapping about it. This is similar to the picture that we showed. We already did atoms, a little bit of the molecules. Now we're at the cellular level, right? And what's inside the cell. Because if what's inside the cell or the organelles get messed up, then of course the cell is going to be messed up. Then the tissue, and then the organ, then systemic, and then this poor little girl is then what? Pathologic, is sick, and then now we have to go deal with it. So it's better to know and understand at that level. And it's the same thing for Alzheimer's, right? Let's replace this little girl with a 55-year-old female whose chief complaint is dementia. Dementia is the progressive loss of memory. And it's not just normal memory. It's you start, an example was my aunt who, I call her my aunt, but she's actually my mother's laboratory partner, and they went through residency together. So she grew up like a sister to my mother. So I always call her my aunt. All of us have extended family. And a classic example of dementia, because of the tangles at the molecular and cellular level, messed up the tissue, messed up the organ, which is the brain. And one day, she had a very good pediatric practice in San Diego, California, and she had it for like 10 years. And one day she was driving to her practice and couldn't find it. She knew something was wrong. She pulled over. She speed dialed her secretary, and the secretary, after hearing it, was a medical assistant and knew what the heck was going on. Called 911. Okay, so you could see how it was a chain of events. But in the case of Alzheimer's, it's genetic, unfortunately, right? Her mother as well also had dementia, uh, um, but and it was sad to watch her over time start forgetting things. By the time I got to her a couple of months later, about 6 months later, I was able to visit California. I was able to visit her with her two daughters. I grew up with her daughters like they were my sisters when we were all living in New York City. And she couldn't remember the names of her daughters, and she thought I was one of her residents. It was a very sad, sad day. And it's all because of what? The cell structure, the cell function started failing, then the tissue function started failing, and then the overall organism. And Alzheimer's, it spreads because we now know that the brain is our control center, so it's going to start messing up a whole bunch of other things. Right now, it's been several years. Several years later, she's still alive, but she can't walk. She can't do anything. She has absolutely no control over any body functions. She's pretty much a vegetable. Um, and it's because why? The progressive means getting worse. The progressive nature of something like Alzheimer's. Now there's a nice tutorial here. Your these notes. We'll talk about this momentarily. A nice side note for the different types of cells. And let me see if they have here. Oh, it's the same thing. Here you go. This one right here, the Carolina notes. There are notes in here that are nice. You could look at them, and they're going to go through the same thing that I'm going to go through. Actually, it has a lovely chart here. Doesn't this look like a beautiful matching question? I could ask you, identify the structure, and then you can identify the function, or I could ask you, hey, what's the function? And you could give me the structure. So remember, when you study, you got to learn things both ways. So this is essentially, these are really nice notes, and they're located in your task 3 in this section right here, cell structure and function, Carolina Lab. So let's now get right to it. And let's find a nice picture, maybe in your textbook. Yeah, let's use your textbook. So we go here, we go in our textbook, and let's find, you go down here to table of contents and overview anatomy, structure, functions of human life, homeostasis, elements, actions, we already went that. Okay, cytoplasm and cellular organisms. I like going over the things on the inside first, and then I'm gonna like talking about the outside. So how easy would it be to take this lovely picture, right? Put it in like Microsoft Paint and erase all these words and just put A, B, C, D, E, F, G. It would be easy, right? So later on this morning, right? Why don't you do that? And then every day for a couple of minutes, you practice. And then what'll happen? You'll get to learn all the structures. And isn't that half of the class? And then I showed you a list that had the organelle, or the little organ in this little beastie, this little cell, and then that had structure. Could you do that and match up with that? Yeah, right. So that's pretty much what we're doing today, and that's anatomy and physiology, isn't it? And could you not preempt me and figure that out before midterm? Hint, hint. That's how this portion of the show is going to go down for your midterm. So you have what? 2 weeks. 2 weeks to figure that out, right? 14 days. And every day you should be doing something. That's why even though the class ends like, the lecture is barely an hour, you have all this other time, and you should allot time every day. And to preempt me and start doing this, way before the day or two before the exam, which is what most people do. And if you do that, you may do well in the exam, but what happens when you go out in the real world and the doctor starts quizzing you on mitochondrial diseases and you know that it's one of the organelles, but you don't know what it does. So let's look at all the parts right now. And of course, you could read everything word for word, but I'm telling you, you're gonna get sleepy. The best way to use any textbook is you use it as a reference and as a guide, like a map. Like when you look at the map, you don't look at every single road and every single thing. You look at only the road that you want, that's pertinent to you and pertinent to what you need to do. So we now know we need to know the organelles, the little organs, or all these little parts in this picture, and their function. So the first one that they talked about right off the bat, right here, cytosol, or cytoplasm. Now the cytoplasm, all of this stuff in here is in a jelly-like fluid, okay? And you need this jelly-like fluid because if it was water, everything would just float around, or we already talked about water, it would just dissipate or become soluble. And that's not good. We need things separate. And all of that, the cytosol, all that substance forms this cytoplasm. Now, this big purple thing right here, this big circle, is the nucleus. And within this big purple circle is a darker, more purple circle in here. So this big purple is the nucleus. And if you see all these little strands, that is all DNA, deoxyribonucleic acid. And DNA is the blueprint of who we are, not only of what the cell is, but the tissue of everything. The nucleus knows when you were born. The nucleus knows when you're going to die. The nucleus knows everything, and it's coded. And we'll be talking about it next week on how it's amazing how all of that fits in here. Now, if you look at the nucleus as a whole, everything on the outside here is loose DNA, also known as chromatin. And we talked about bonds last week. DNA has a lot of hydrogen bonds, and we talked about how the hydrogen bonds are weak. And if they're weak, that means they can be compressed and then they can be relaxed. So the chromatin is the relaxed DNA. It's the DNA, the working DNA that we need for the cell to do its business, because we need to know the blueprint. We need to know the plan of what this cell is going to be and how this cell is going to interact with the rest of my body. All your nucleated cells in your entire body have a nucleus, and this nucleus has chromatin, and that is the loose DNA. Now, all the DNA that I don't readily need, that's all tightly packed here in the nucleolus. So the nucleolus is the tightly packed DNA. That's the stuff I use for storage. But the chromatin is the loosely packed DNA. That's the working DNA that I need. Now, last week's lecture, we talked about RNA. RNA is the messenger, or the ribonucleic acid, because the blueprint is kind of on a different code. It's speaking a different language. And the RNA translates that language to all these little bumps here. You see all these little bumps? That's a bump. And all these here in this thing here, this structure here, are bumps. All these little bumps or all these little circles are called ribosomes. Those are protein makers, or protein factory workers. And the protein factory is this thing called your rough endoplasmic reticulum, or RER. The RER, or the rough endoplasmic reticulum, we know it's rough because it's got all these little bumps. And those bumps are ribosomes. So this is how it goes down. The nucleolus lets go or relax some DNA. The DNA, now relaxed, is now called chromatin. The code in the chromatin, in the DNA here, gets shared with the RNA. The RNA then gives the message to the ribosome, and then the ribosome takes that message and makes proteins. So what could I ask you? What's in the nucleus? You'll tell me DNA. What's in the nucleolus? Tightly packed DNA. What's chromatin? Loose DNA, or loosened DNA. What's ribosomes? Oh, that's the protein factory worker. They could be floating around by themselves like an independent contractor, or they could be affiliated with this rough endoplasmic reticulum, which is the protein factory. Now, if we have a rough endoplasmic reticulum here, you also have a smooth endoplasmic reticulum. The smooth endoplasmic reticulum is another type of factory, but it does other things. Remember we talked about proteins, carbohydrates, and fats? Well, the rough endoplasmic reticulum, that deals with proteins. The smooth endoplasmic reticulum deals with carbohydrates and makes carbohydrates and fats. So can you see now how easy my exam is starting to unfold? And can you make a multiple choice question examination on your own to preempt me and to figure this stuff out? Sure, sure you can. Or heck, I'm going to do one better for you next week. I'm going to give you last term's midterm so you can know what it looks like. Of course, it won't be the same exact midterm, but it's going to look pretty similar, right? So to recap, chromatin, nucleolus, nucleus. And if you could see, the nucleus has a membrane. It has a wall. And then you have your rough endoplasmic reticulum, smooth endoplasmic reticulum, and you have these loose ribosomes here. Now, remember we talked about the cytosol? That's all this fluid here, this light yellow stuff, in this thing called your cytoplasm. It surrounds everything. You can also see these little, like, the best way to put it is they're like scaffolds. And you know scaffolding on a building? It's like extra structure. They're formed by microtubules. Microtubules are formed by proteins. And they give the shape of the cell. And if you recall, week 1, we talked about how the shape mimics the function. And guess where all of that information starts? It all starts here in the nucleus. And the nucleus is so important that it has its own skin, the nuclear membrane, which is this dark line right here. Okay? Now, to relate it to what's going on with viruses, right? And the mask debate. Yes, you should wear your mask. It is the law, wear the mask. But to think that the mask somehow protects you from a virus that's 12 kilodaltons big, this is what viruses do. It'll go right through this, right through the cytosol, right through here, and then go in here and hijack either your RNA or your DNA. And remember, the RNA and the DNA have the blueprint of who you are. Well, this is how insidious and how horrible viruses are. The virus will hijack the RNA and tell the RNA, hey, don't listen to those instructions. Listen to these instructions. These instructions are cooler. And the RNA will be like, okay. Or if it hijacks DNA, it will go here in the loose chromatin and change it. And then now the blueprint is different. So before, the blueprint was saying, oh, be a heart cell, right? But now it says, oh no, we're going to be a virus making factory now, because that's what the blueprint is now. So that's why viruses are very hard to cure and they're very hard to prevent. But we also know, and I believe it's the beginning of Anatomy and Physiology 2, when we talk about specific and non-specific immunity, we now know that in order for you to be sick, and I believe you guys also watched the video on that regarding the chain of infection, in order for you to be sick, you have to be a susceptible host, meaning you have to lower your immune system. And how do you do that? Well, one of the ways is you lower your barriers. So one way we could increase our barrier is to wear a mask, not necessarily for the virus itself, but for the 249 other pathogens that's going to attack my system on a daily basis and then lower my immune system, and then I get sick. And I've quoted the statistic, and if you need to see it, I can email it to you, to fight and combat the stupidity that's going on right now on TV. I cannot watch TV or look at things on the internet. And if you're getting your information, and that's why we do discussions, if you're getting your information from Instagram and Facebook, you really need to reconsider your role in the healthcare world, because there's a lot of garbage floating around, even on physician updates. I don't know if I shared with you guys last week, I just went through the Harvard COVID updates and spent a penny to attend this 4-hour meeting. It had Dr. Fauci, it had everybody in it. It was rife with politics, and it's funny that I had colleagues from Michigan, I had colleagues from New York who were begging the host to tell us, can someone please give us diagnostic criteria and diagnostic data regarding the testing? Like, how do we know that the test works and it's even remotely efficacious? None of us have any answers. Actually, many of the physicians that are on that call, even after spending $500, they logged off because they knew it was political BS. And it was frightening because this is a medical college and a medical institution that's now handing us politics instead of handing us answers. And that's why we do discussions. And that's why I'm promoting discussions and really looking at where are you getting your source of information? Because all of this, it goes, the way we look at medicine is data. And imagine all this data right here. There's nothing but data, your DNA. Imagine if it got hijacked by something that's telling it to do something else. Okay? And that's how insidious, and that's why you get a common cold, you can get it again if you're immunocompromised. And we'll be talking about in anatomy and physiology too, how also viruses trick immune systems to sneak in. They're not only very, very small, they adapt their cell wall, which is that's another insidious thing they do. And remember, a virus isn't a good or bad thing. A bacteria is not a good or bad thing. It's just a living organism that wants to live. And this is its way to do it. So in a way, it's kind of like a parasite. Now, another part of the microtubule system, which is the scaffolding system that gives shape to your cell, along with the cytosol and the cytoplasm, is this thing here, these centrosomes. These centrosomes, they align up on, there's two of them, they align up on either side of the cell when it's time for the cell to start dividing. And it organizes the cell, and we're going to talk more about that when we talk about mitosis and meiosis. Now, this is a little beastie, so this is the brain. This is the protein factory. Well, this is the carbohydrate and fat factory. Now, remember that the cytosol is like gel-like. It's not fluid, so things can't just float around. So just like in Jello, like if things were just on its own, like ribosomes, they kind of get stuck unless they were packaged. And that's what this Golgi apparatus is. The Golgi apparatus is like the mailbox or the post office. And what does the post office do? It takes a package and it has a to and a from. It takes it packages things in Golgi vesicles, or these little bubbles, and with instructions where things should go. So, for example, it could be garbage. So the message would be, the addressee would be what? To go shove it outside. Or it could be something that the other organelles need. And so it goes to that. One thing that the organelles need is energy. So the Golgi apparatus, think this is the brains, this is the protein factory, this is the carbohydrate and lipid factory. Golgi apparatus is the post office. Okay. Now, something's got to power all of this because it's a living, breathing thing. And what I mean by breathing, yes, it takes in oxygen and it takes in glucose. Oxygen, of course, that's the thing we breathe. And there's cellular respiration. It goes at the cellular and molecular level. So we need oxygen. So the mitochondria takes that in. Vesicles will package it and float it towards their way. We also need glucose. We eat a meal, right? It's composed of all different kinds of sugars, and then our body metabolizes things, right? Breaks it down. Meta means change. Bol means growth. And then the Golgi, right? From here, they package it, and then they send the glucose to the mitochondria. So the oxygen and the glucose goes into the mitochondria, and the mitochondria is the powerhouse of the cell. It supplies power. It keeps the lights on. It keeps everything running. And I believe our discussion today is about mitochondria. The discussion that's due next week, I think it's about mitochondrial disease. So you can now kind of imagine, even before you research it, that okay, it's going to affect my energy level. Now, oxygen plus glucose equals ATP, or adenosine triphosphate. And what does that look like? It looks like so. Okay. Now, ATP, adenosine triphosphate. So you got you have an adenosine group here, and you have 3 phosphate bonds, not blondes. Geez, what am I thinking about? Right now, phosphate bonds. Okay. Remember, we talked about how bonds, they have energies, and phosphate bonds are high energy products. Here's a simpler way to look at it. Pretty pictures. Now, ATP, 3 of them. So every time it goes through a hydrolysis reaction, which requires water, and you see this Illuminati stuff that's going on? Oxygen, water, glucose. Isn't that the stuff that we do all day? I breathe, I drink water, and I eat food. And that keeps me alive. And it is the mitochondria that processes it. And when it does it, it chops off this bond and it releases energy. And that's how your muscles work, how your heart works, and that's how your whole entire body works. And we know that if I don't eat, if I don't breathe, if I don't drink, what happens? I don't function very well. So ATP is the molecular food of your body. Okay? And looky here, it's made out of a sugar as well. Adenosine triphosphate, ribose group, 5-carbon sugar, but we take glucose, which is a 6-carbon sugar, oxygen, and water to break this bond and then to do what? To process it. So ATP turns into ADP, adenosine diphosphate, and then we chop it again. It turns into AMP, which is adenosine monophosphate, and then we chop another bond again, and then it gets recycled. And as long as you keep on sucking in oxygen, breathing, and then drinking water, right, H2O, for the hydrolysis reaction, and keep on eating food that gets broken down into the 6-carbon sugar glucose, then ATP will always be there and you will be alive. The second you stop doing any of those, then the mitochondria stops making energy, stops telling everybody to do, because if we turn off all the lights, none of this will work. So next, lysosomes, peroxisomes. There's a lot of garbage floating around here, waste products. And the waste product of mitochondria is carbon dioxide. So we have to break some of that down, and the Golgi apparatus then informs them and packages them to have it as a secretory vessel to throw things out. Now, I don't want you to get the impression that all the cell does is throw out garbage all day. It doesn't, but the lysosome is there to break things down because we needed to break down that glucose to get into here, right? And the peroxisomes also, you've heard of peroxide and superoxides, they break down things too. So we got to break down garbage and also break down foreign body. So typically, let's say if some foreign body, let's say this cursor, this arrow here is a bacteria, it'll go in here and your cell will sense it as foreign, and then it will, the Golgi apparatus will send some peroxisomes or lysosomes to break things down. And then any products will be then secreted out. Another thing that the secretory vesicle does is, let's say this cell makes hormones. Let's say this cell, this is a beta cell of your pancreatic cells. Okay, your beta cell, in its DNA, it says, hey, make insulin, make insulin. Okay, guess what the protein factory does? It makes insulin and then gets packaged by the Golgi apparatus. And then they make these Golgi vesicles full of insulin. And then it gets secreted out when you've eaten a big meal. And when you've eaten a big meal, you've got tons of glucose in your sugar. I mean, glucose in your sugar or glucose in your blood. And that glucose has to go into the mitochondria. But the problem is glucose is this big chunky cell, so we need insulin, which is the key to open the door so that big fat glucose can go in, and then the mitochondria and the lysosome can break it down. and they use something called the electron transport chain, and they break things down, and then it creates ATP. Vacuole is also kind of like an extension of the Golgi vesicles, and vacuoles, we kind of use it as storage, right? Hold up, my son's goofing around. Hey, Nelson Hermie, shouldn't you be doing sections? All right, sorry about that. The challenges of having your kids be in relatively the same room as you. So you could let's review on how I could ask a question. Could I take this and ask a quiz? And how's this? Let's even look up an organelle quiz. I don't have the time to make one. Can I look up one? Sure. Let's find one. Oh, look at this. Let's take this. Where's my Microsoft Word? Ow, bad. It wants me to get the original file. All right. Oh, it's part of Quizlet. Oh, Quizlets are cool. So do you think we could like take this quiz and then we could ask, oh, these little strands of DNA, right? What are those, right? What's on the I guess what's on the outside? Let's find a better one. I don't like that one. Too small and nope. Yeah, here you go. This is a much easier representation. Let me open it up. Oh, everyone wants a free account, which is not really free. Copy image. And here you go. So I could take this. And do you think I could take my own quiz? Yeah. So I could point at this thing. It's in the middle. So that's got to be, let's insert text box. So I could ask, let's make this, it doesn't want to play me. Let's make this A, B, and C. So this is A, B, and C. So just by looking at this, which one of these, A, B, and C, is the nucleolus? I'll give you guys a second. Have an answer in your mind. And the answer is B. Where's the location of the chromatin? The answer is, give you a second to think about it, A. Identify the nuclear membrane. And it's what? The dark line that's, and the thing as a whole, or identify the nucleus as a whole, and it would be this arrow, be everything. You have your smooth endoplasmic reticulum, rough endoplasmic reticulum. I could be pointing at this. This is the ribosome. Remember the protein factory worker? So you could easily do this at home, and you could see how, imagine if you just took 5 minutes every morning before you get to work or before you do stuff. And what will happen by the end of the week? Then you have it on lock, and it'll be easy. And then, more importantly, you get to know it. Okay? So that's essentially all these notes, if you want to go through all of those. But I don't think so. It's easier to have that diagram that we had. And you could see here how the cytoskeleton is just simply made up of little bits of protein. So that's a part of a protein. That's a part of a protein. Actually, they're all amino acids. And then you put them all together. Remember our lecture last week? Amino acids, just think of each one of these as an amino acid. You link them together in a peptide bond and you have what? It's a protein. So all of this is proteins. Your hair, all of it. And that's why I find it very silly when people say, oh, you can't have any protein in your diet. It's insane. You have to have everything in your diet. Oh, you could see there's a defensive wall in the nuclear wall, but you could also see that there's little channels, and that's how you could see how easy something that's, oh, by the way, what does 17 kilodaltons look like? It's smaller than this ribosome. It would be probably 2 pixels on this screen, so you could see how easy a virus gets through. That's why I'm ordering a mask, and it's that clearly states that it's not really protecting you against a virus. It's protecting you against the other things that would lower your immune system to get a virus. What else? Oh, here's another thing that we showed you. Remember the chromatin, right? Chromosomes, right, are who you are. A human being has like 46 of them, 23 from mommy, 23 from daddy. And then they're all made up of a whole bunch of chromatin. And histones are balled up DNA. Okay, so you could see that all of it is what? Code. And next week, we're going to be talking about this code. It's a double-stranded code, right? And the DNA, it's a blueprint of who you are. Okay, we're going to talk way more about this next week and all those wonderful little pictures. But right now, let's get back to the last thing that I talked about, that I said I was going to talk about. I was going to talk about the this lovely, lovely picture, which is my favorite picture of the cell membrane. Okay, and it has a chock full of things. So you'll see the cell membrane is made up of these little heads with these little tails. Does everyone see that? And it's made up of like a mosaic. So it's like a whole bunch of things all put together. If you've ever seen mosaic art, what's a mosaic? When you look at like mosaic art, my sister does this kind of weirdo stuff. It's a picture that's made out of what? All these little bits, and that's essentially also what your screen is made out of. If you look really, really, really close, your screen is made up of a whole bunch of pixels. They're really, really small, but you can't really see them because they're really, really small, and there's many of them. Same thing with your cell membrane. And your cell membrane here, and oh, by the way, you see there's gaps. Even before you get into these protein channels, there's gaps. Oh, by the way, how big would a virus be? About half the size of this dot. So it doesn't need the protein channel to go through, but you can go right through this if it wants. If it wants. And also if the immune system allows it. And it can, and it does on a regular basis. If you are immune compromised. So we look at here. Let's look at it from the outside in. Well, first of all, let's look at what this is made out of. So this is made out of, and this representation, a phospholipid bilayer, okay? And it has a hydrophobic tail and a hydrophilic head. And as of last week's lecture, we know that hydrophilic means water-loving, and hydrophobic means water-fearing, or it doesn't like water. And it makes sense because when we look at this, there's water on the outside, there's water on the inside, and there's lipid in the middle to give it a nice insulative layer so that all the stuff on the outside stays on the outside. All the stuff on the inside stays on the inside. And unless we want it to come in and out through these channels, and that's the way we want to keep it, okay? So I could ask you about this phospholipid bilayer. The hydrophilic layer is the phosphate head. It loves water, right? And the hydrophobic tail is filled with fatty acid. And we already know the fatty acids are part and parcel of your fats or your, by the way, you have glycerol and a fatty acid. That's triglycerides, right? So I could ask, What's the head made out of? And you'll say it's a hydrophilic, water-loving. And what's the tails made out of? Hydrophobic. They are they're water-fearing. They don't like water. And that is the cell membrane. It is a phospholipid bilayer. So that's not one, it's two. So whoever built us real smart. They built a wall that's double layered, that's chemically insulated on the inside, and but water loving and water interacting on both sides, the inside and the outside. Now, how do I know which one's the outside? Well, you see here, this is a glycoprotein. Glycoprotein is like a badge or a jacket, right? Along with glycolipids here. But glycoproteins play the greatest part of the role. But whatever's sticking out here gives the cell its chemical identity. That's how your cells know. Didn't you ever wonder how your cells know the good guys from the bad guys? Well, they see each other, quote unquote, see. They don't have eyes, but they sense the chemical nature of all the cells. So if this glycoprotein coat is wrong or off, your immune system should be attacking it because it's not one of the friendlies. It's the same way as uniforms. If you've ever seen, the IR patches on modern uniforms, the infrared patches, like you could shine a light on it and you won't see anything. You can walk around in the dark, but if you have your night vision goggles on, you'll see the patch bright as day, and it screams, "Please do not shoot me. I'm one of the friendlies." Okay. And that's what your body does. And the horrific thing about the glycoprotein coat on viruses, like an example is HIV, it can change, which is horrific. That means that, let's say, for example, I reckon you're wearing a blue jacket and I know that you're the enemy, right? I know blue jacket enemy, I'm going to eat it, right? What if I change it to a purple jacket? Now I can't eat it. Now I'm not sure. And that person can go what? Right into my house, then take over my RNA, and then now tell my cell what to do, and to utilize my own energy, my own mitochondria, my own ATP to do its bidding. So I make it akin to a home invasion, because from the outside, inside it's what? Horrors are going on. On the outside, everything looks business as usual. So I could ask you, what's the function of a glycolipid or glycoprotein coat? It's for identification of what the cell is. What's the function of the hydrophilic head? To interact chemically with the water. There's hydrophilic heads on the inside and on the outside. What's the function of the hydrophobic tail? It's to keep that water on the outside and this water on the inside, unless we have a signal for these protein channels. These are protein channels, here and here. And they open and close depending on what these glycoproteins and glycolipids tell us. Another thing you will also see that's within your cell membrane is cholesterol. Now, cholesterol is not fat, okay? Cholesterol is a vehicle that will take fat or lipids and transport it in and out of cells. And that's where we have the HDL, LDL, VLDL. And again, back to that layperson term, the good cholesterol and bad cholesterol. There's no such thing. There's only your HDL, which is your high density lipoprotein, which laypersons call good cholesterol. That's the cholesterol vehicle that will bring fat out of cells. And we have more VLDLs and LDLs, way more, actually 3 to 4 times more of cholesterol vehicles to bring fat into cells, because fat, when broken down, has glucose. Glucose can enter the mitochondria and then give us energy. But the thing, we as human beings, and especially us Americans, right? I can attest to that, right? Since I'm guilty as charged, we eat way more than what is required, right? And what will happen? There'll be more cholesterol vehicles bringing lipid in, because remember, it's also a survival mode that's built into our DNA. During cave person days, cave men and cave women didn't know when they were going to get their next meal. So fat deposition was a very advantageous thing, right? But now it isn't. We have a grocery and supermarket. So there's a lot of studies that have been done on the Inuit native people, and also known as Eskimos, that layperson term. But the Inuit have high concentrations of LDL and VLDL, and now in the modern world, it's now affecting their heart and their lungs and their kidneys, because now they don't really have to hunt for food and to but their genetics is geared for fat deposition, right? And some of us, we've met people who are like ultra thin, like my son here in the background. He's your classic ectomorph. My boys, they're ectomorphs. They can go to buffet and not gain a pound, because that is their body structure. Me, I even think about food, I can gain weight. And that's the challenge of genetics. But knowing and understanding the pathophysiology, what can you do? You can modify it. So that's why I have to work out every day. That's why I have to, every little thing that I'm drinking and eating, I have to watch out for. And no matter what I do, I'm only in my early 50s and I'm already pre-diabetic, even though I do all of the above, because my genetics, or remember your chromatin, your DNA, that's what it wants you to do. But you have to do what? There's moments you have to fight all of that. And it's the same thing with behaviors. It's because it's all programmed. But if you know it, then you could do management. And remember, medical management is just a part of it. Taking meds and things of that matter. I am from the Department of Internal Medicine, and I don't promote meds. I promote adjusting your lifestyle. That's way better than having to take medication all day. Now, all these glycoproteins and glycolipids, and also the door, which is the protein channel here. Nelson, can you lower the sound, please? These doors have receptors, and remember we talked about how the enzymes have a lock and key fit. Well, it is an enzymatic function, these receptors and these glycoprotein coats. So let's use insulin as an example. Insulin latches onto the glycoprotein coat that's affiliated with a channel protein. And then it acts like a key to open up the door so that glucose, which is a big fat thing, can't fit through these little spaces. But if I open up a protein channel made specifically for glucose, whoop, it goes in. Oh, by the way, I just mentioned that I like for a diabetic, you could sit there and take insulin all day so that the glucose can go inside the cell so it can be utilized. But how's this, right? I have a lot of sugar out here. How do I decrease the sugar on the outside? Well, less intake of sugar. That's one way. And another way is I got to work out. I have to not only sweat, I have to really, really, be challenged. If you're on the treadmill, maybe I've already said this before. I am a broken record regarding this matter. One of my pet peeves in the gym are people who hang out and just be social. In my opinion, it defeats the purpose. I go to the gym, I go 50 minutes and then I'm out. I burn a lot of calories, anywhere from 250 to 300 within that 50 minutes to an hour, right? And I leave. I don't sit there, I don't hang out, I don't talk, right? But that's just my personality. Another way to get that sugar in here is exercise. If you exercise, it goes, and you have to be at your max heart rate and above, right? And if you exercise, it opens up these doors, and guess what? Sugar goes in, because your mitochondria knows, hey, I need ATP for my muscles. So, hey, open these things up. And those are your GLUT2, GLUT3 protein channels, and they're in all of your cells. So that's why, even though I'm pre-diabetic, I don't have to take any diabetic medication, because what am I doing? I am changing my diet, decreasing the sugar out here, and also I work out, I run or swim every day, as in every day, 7 days a week, right? But I have off and on days, meaning that I won't run as hard or I won't swim as long on the days on my off days, or I decrease the incline, or like last night, I increased the incline. oh, jogging and just pushing up the incline is just murder. And what will it do? It makes you work out more. And what will it open up? GLUT2, GLUT3 proteins, glycoproteins, and then the sugar can go in instead of juicing myself with insulin all day. Medicine, 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 medicine. That's not fun. You also have peripheral and or integral protein. An integral protein is all the way through, and a peripheral membrane protein is only partial way through, and it's part of the structure of to keep the shape and keep the structure of your cell wall here. So you could see now, I just spent the last, I don't know, 12 minutes just talking about just your cell wall. And this is your cell wall, also known as the gatekeeper. So now you could see how it's going to let some things in, let some things out, but it's protecting. And that's why it's called the gatekeeper of the cell. That's why penicillins are so effective. Let's say this was the cell wall of a bacteria that I don't like. Penicillin pokes holes in your cell wall, and then now what will happen? Water will go in, water will go out, things will go in, things will go out, and what will happen to the cell, or to the bacterial cell? It'll die. Okay, so passive and active transport, just know that transportation has to be, passive transportation is, let's go back to this. Passive transportation is when there's a higher concentration out here and a lower concentration out here. Let's say, for example, I ate a meal, higher concentration of glucose out here, so the insulin will signal the doors to open, and then what will happen? Glucose from a high concentration to a low concentration will fall right in. But there are times that, especially in muscle contraction, I'm going to need certain ions like sodium and calcium and potassium to go in and out of the cell on purpose and against the gradient, and that's active. And that means these protein channels are connected to, they pump things and they require energy, because if you pump against the gradient or you pump uphill, you're going to need power. And of course, power in the source of ATP, adenosine triphosphate. Hey, how many times did I mention adenosine triphosphate already? So what are the odds it's going to be on the exam? Pretty good, huh? Right? Look at here, and here's a protein channel. It can let things in, let things out, because it is, there are doors. And this is just a quick example. We talked about hypertonic and hypotonic in the chemistry lecture. We need to be in the middle, always. There always should be water balance. If I have a hypertonic solution, right, the water outside my cells, it's going to draw, that means it's going to have a lot of salt. It's going to draw all the water out, because remember, water water goes wherever salt goes. So if there's salt all in this black area here, right, in your plasma, it's going to draw all the water out. You're going to have then you're going to have a crenation of your red blood cells. Now, if there's a hypotonic, right, all the water is going to go in, and then your blood cells are going to get all puffed up. If it's all puffed up, can anything sit on this thing? No, and then you're going to have some problems. Where do we need to be? Water balance. Equal amount of water going in, equal amount of water going out, and this red blood cell here then can do its job, which is to carry oxygen, carbon dioxide, proteins, sugars, and whatnot. So that's why if you don't hydrate yourself, you get hypertonic very easily. If you overhydrate yourself, hypotonic. And that's why, again, especially with the nursing staff, it's a pet peeve for nurses if you do not properly monitor the fluid intake and outtake of your patient. Because after a while, it seems like a chore, but it's real important. And you can now see also the importance of the cell membrane in doing what? Maintaining an isotonic solution, maintaining the water balance. Okay. Here's an example of a sodium potassium pump. So the pump, it's closed. I want sodium to do what? It goes to go out, but I have to pump against the gradient. So if I have to pump against the gradient, I need power in the form of ATP. And where did I get the ATP from? I got it from the mitochondria that's inside my cell. And this is exactly right here, this little picture here, sodium and potassium. Sodium typically turns muscles on. Potassium typically turns muscles off, right? So if I want to increase the sodium in my patient's blood, right, I put a line in them, right, and it will, in theory, increase contractility of my heart muscle. But if I want to slow it down, I juice them with potassium. Oh, by the way, how do we do lethal injection? I flush the patient with potassium iodide, and then what will it tell my heart? It'll tell my heart to do what? Stop permanently. Okay. This is a nice little example of how vesicles get rid of stuff, how it pinches against the wall. And how does it know? Because the inside of the cell wall looks like the outside of the cell wall. They have glycoproteins on the inside. They have glycoproteins also on the outside. And that's how it knows chemically what to throw out and what to bring in. And it's crazy complicated. But now you know how complicated just this little cell is. Okay, so let's look at, did we go over everything we needed to go over? Let's see. Oops, not task 2. I'm living in the past. This is the future, or the present, actually. So let's look at our goals. Did we talk about cell theory? Yes, this all has been cell theory. The cells have a job. It has a brain, and the brain tells it what's its job. And it's organized. We talked about the cell membrane, cytoplasm, and all the cellular organisms and their organization. Isn't that the cell structure, organelles, and the function of organelles? And that's what your concept map, which is due next week. Now, let's go through the type of cells and let's call it a day. Okay. The types of cells that we now talked about are prokaryotes, eukaryotes, and viruses. Viruses, we already discussed. Let's look at virus real quick. Now, the viruses, examples are hepatitis, HIV, measles. And the thing about the virus is that viruses are very, very small because they don't need much, because they're essentially parasites. They can use either the DNA or the RNA in the nucleus to do their bidding. And there's some that use DNA, there's some that use RNA, and HIV is the classic one that gets studied, and that's what they call a retrovirus. It goes backwards. Now, what do I mean by that? Remember we talked about how it goes from DNA to RNA, then to the ribosomes, right? Well, HIV hijacks the RNA, and then the RNA backs up the message to the DNA, changes the DNA message, and then it goes back down the chain to the ribosomes, and then the ribosomes then make a whole bunch of HIV. Okay? So that's essentially a virus. Think of it like as kind of like a parasite. Now, talked about cells. Let's talk about what's a prokaryote. Now, a prokaryote, I want you to think of its simpler cell. Okay, it's simple in many, many ways. And the prokaryotes, I want you to think bacteria. Okay, and if you look at bacteria, it's going to have these names, and it's going to be I forgot which one is like family name or whatever, but whatever it is, it's going to be the first name will be capitalized and the second name will be lowercase, and it will be in italicized. Okay, so these things are very, very simple, and they have similar organelles. But the difference is they have a very different kind of plasma membrane. Their plasma membrane is a lipid. It's a barrier, but it's a glycocalyx. It's a glucose-based barrier, so it's not biphospholipid like human beings. But they have all the same things, right? As the that's a eukaryote. The prokaryote, I want you to think bacteria, and then they have just think simpler. Now, who are we? We are eukaryotes. And the way I remember it is you. You are a human being, therefore you should have all these organelles and whatnot. We already discussed all of that, right? So the prokaryotes can invade a eukaryote. Virus can invade a eukaryote. And actually, we have a whole bunch of prokaryotes that are inside our body. And that's what the laypersons call, like, the biotics or the good bacteria. There's no such thing as good and bad bacteria. There's only bacteria in the right place and in the right amount. And I believe I already talked about E. coli or Escherichia coli. The E is, of course, capitalized in coli, and coli means where? Your colon. The only place your E. coli should be is in your colon or your large intestine, okay? Now, if you don't wash your hands and you scratch your butt, and then you make me a sandwich and then I eat it, then we got a problem. Because now E. coli is in places other than the colon, and that's how you get sick, when you get a bad streak taco and then you get gastritis or bacterial gastritis. And it's the same thing. Right now, in the air, there's tons of viruses. There's other things that can easily kill you. Respiratory syncytial virus is present in 40% of people. But why doesn't it kill you? It doesn't kill you, right? If you keep yourself healthy and non-immunocompromised. But RSV in a baby, good luck. It's not, and especially a baby that has any spinal defect or any, they were born with any other defects, the mortality rate skyrockets after that. Okay, so these are the things that we as medical professionals now have to start looking at the world differently, right? But you don't want to say that to typical laypersons, or you don't want to put that on CNN, because if people start figuring out there are other viruses that will potentially kill you, and that was also my other question. How specific are the new, is the testing kits? Because there could be cross specificity with other coronaviridae. Ooh, by the way, your typical cold is, guess what? It is a coronavirus. And there's 342 strains of those. So how do you know that this thing isn't picking up, these tests aren't picking up the wrong virus? Because they have similar glycoprotein codes. But of course, no one has an answer for me, so I just walk around life and guessing, just like the rest of y'all. And that's not how medical professionals live, is it? And that's why it's very disturbing. Just to add to the conspiracy theories. Okay. And watch this. What is the discussion that's due next week? Watch this and discuss how mitochondria is affected in her disease. Now, so watch the video and then relate it back to whatever citation do you have it from. Several of you, and you know who you are, I put the comment in. Some of you just put in whatever, like you do something like this, right? You watch the video and you make your statement based on the video, and then you do this. You Google mitochondrial disease. Then you remember my lecture. Oh, Dr. Garais only likes, umdf.org, and you pick this, and then you cite it, but you don't use it. You know what I'm saying? Right? And then that's not the way to do citations. Citations are to support you when you say things, right? So if I say things like, my patient is tired all the time because according to the United Mitochondrial Disease Foundation is that mitochondrial disease affects the conversion of food and oxygen. If you don't have any food and oxygen, according to Dr. Garais' lecture and the United Mitochondrial Disease, do you see how it's now backing you up? He goes, I won't have any energy. I won't have adenosine triphosphate. And if that, he goes, then I'm going to have a whole bunch of dysfunction in a whole bunch of places. And one place is muscle. I'm going to have some weakness. I could also have diabetic problems. I could have cardiomyopathies. Do you see how I'm using this website, but I'm not cutting and pasting? There was another student in my class, my 120 class the other day, who she pretty much did this. That copy pasted. She cited it and then put quotations on everything. Don't do that, because if you quote something, make sure it's less than 10% of your entire thing. So if your submission is 200 words, don't pick a quote that's 150 words long. Use your paraphrasing powers. And what's paraphrasing? You take bits and pieces, right, and you make it your own. Like, instead of using the word cardiomyopathy, you just say that mitochondrial disease can promote heart disease. Mitochondrial, instead of hearing loss, mitochondrial can promote deafness, right? Use other synonyms, right? And you could see, just by looking that up, it took me 2 seconds. And then I now have a whole bunch of things that I can now expand upon, right? Oh, if I want to learn more, I could view the paper, and then I could see, and it'll expand itself. And then now, see that other website? It looked kind of, even though it's from a .org, it looked kind of layperson-y, right? You know? Ooh, look at this. Every 30 minutes, a child will be born will develop a mitochondrial disease, right? I find it very, very interesting how everybody is focusing on the wrong diseases. Did you guys hear every once in a while they keep on talking about how COVID disproportionately affects Latin people and African Americans? I'd be way more worried about the effects of diabetes and kidney disease for an African American patient. COVID would be as an internist who practiced in New York City, I'm way more worried about that. Way more. But the world loves drama. Drama. We gotta love, because we love our drama, and that's the latest drama. So when you do your discussion, it doesn't have to be long. Some of you write me book reports, like 1,000 words, 1,200 words. I could ask for a tutoring session. I could show you how to chop that down to 300 words. It's called conservation of it's called conservation of speech. In the medical world, you should say things simply and concise, instead of using elaborate language. And if you have one example and it matches up the citation and it relates to the video and relates to this lesson, boom, easy peasy. Well, not easy peasy, it's a skill set. I keep on saying easy peasy, but this is a lovely video here, and you could see it has a built-in quiz. You think you could easily do that? Sure. And these videos mimic all the stuff. I don't like this video. There's better ribosome videos out there that you can look at. Don't do the lab, of course. By the way, we won't even do this in laboratory, because I've been doing this laboratory for 10 years. This osmosis diffusion never worked. But the cell structure function, I think it's a mimicking of the other notes. It's the same thing. These are wonderful notes. They condense your textbook. Now, the application assignment, you click on that, click download the case, and we look. Bringing home baby. So do part 1, questions 1 through 5. Part 2, questions 1 through 7 should be good enough. And then, of course, read part 3. Oh, this is lovely. Totally forgot this was here. This is a nice way to practice. This is another picture we can practice on. But what most likely would be the picture I'll use, the picture in your textbook. And that's easy. I could easily copy and paste that. Now, let's look at this before we call it a day. They typically, I find it very silly why they use Lay syndrome. Why couldn't we use sickle cell anemia? That's a little bit more apropos to this lesson. But whoever was doing this wanted to be clever and use a disease that no one knows. But it's the same idea. These are your chromosomes, right? Chromosomes, chromatin, your genetic material. You get one set from daddy, one set from mommy. And this is called, these letters are called genotypes. The genotypes represent what physically they're going to look like, and that what their physical representation or your signs of symptoms of whatever's going on, that's your phenotype. So if you could see here, this is a case of a genotype that's recessive and that's dominant. If it's a capital letter, it's a dominant thing. And if it's a lowercase letter, it's a recessive thing. So if you have two parents that have heterozygous, meaning they have one dominant gene, one recessive gene, one dominant gene, one recessive gene, in this particular Leigh syndrome, also in sickle cell trait, they're unaffected, they're asymptomatic, but they are carriers. Now, if these two get together and have some babies, the odds of one child being unaffected is 1 in 4, or 25%. The chances of a child to be affected, but they'll be heterozygous, dominant, is 2 in 4, or 50%. And the chance of the offspring to be homozygous recessive, and they're going to have the full-blown disease. So if we were talking about sickle cell trait, daddy and mommy have sickle cell trait, 1 in 4 chance that the child will be perfectly normal, no sickle cell problems. 2 of them will have sickle cell trait. They may be asymptomatic, or they may have some minor symptoms, and one's going to be outright sickle cell disease, and that's homozygous recessive. So you have homozygous recessive, heterozygous dominant, which is your carriers, and then you have your homozygous dominant, which is your perfectly normal offspring without any disease. And that's how autosomal recessive inheritance works. Okay? With that being said, again, to reiterate, do only part 1, questions 1 through 5. Part 2, questions 1 through 7, and that's next week. That's it. Now, it is at this point, there was no questions. It was at this point of the show. Let me see who's here. All the usual suspects. Right? And I'm recording it for prosperity. And for those of you who are watching this video, one last public service announcement. In order to garner attendance during the week, of course, you can attend this and you automatically have attendance, or you do one of the things that are due before around Saturday, 12 noon, 3-ish. That's when I'm supposed to post attendance, but many times I hold out till like Sunday morning. So please get something done. And if you didn't attend this lecture, because there's some people who are working and they can't attend the lecture all the time, but you still can get credit. And remember, another public service announcement, I'm sorry, but I'm getting a lot of late submissions. Every day you're late, that's 10% off. So things are due today. So you submit it in tomorrow, that's what? Minus 10%. You submit it Friday, minus 10. Saturday, minus 10. Sunday, minus 10. By next week, you're down to what? 30%. But again, please, I implore you. At the end of the day, I am merely a secretary. I just jot down what you did or what you didn't do. Okay?